I'm Phani Dathar. Today we want to talk about how do we use knowledge graphs and Neo4j and all the tooling in the Neo4j ecosystem to take these GenAI applications to the next level and make them enterprise ready, and even transform GenAI applications um, for the things that we wanted to achieve and go beyond a simple or a search application. So to give you just a high level of what we are going to talk about today, every one of us, I hope every one of us have seen some flavor of an application interacting with a large language model, whether you're trying to search through unstructured data or whether you're trying to learn how these LLMs work or how the agentic AI work or what the MCP is all about, and so on and so forth. But at a basic level, when it all started with ChatGPT back in November 2022, people were thinking, I don't need anything else. All I need to do is take my application, interface it with the large language models, and I should be able to expose it to the customers. I mean, the promise was like that. However, as with every other technology, we started to see that it is not enough because the enterprise data or the our personal data is not exposed, or even if it's exposed, the questions are not personalized to the content that we want to serve to our customers. So then started with RAG. RAG is where retrieval augmented generation, where there is a data source that is providing all the relevant context for the questions the users are asking, so that the LLMs can not just go answer whatever they know about the question, but focus the question on focus the question or only use the data that's provided as a context and answer the question. So enterprise, but that is still in a very nascent stage, because what kind of data source do we need? How do we use security, right kind of security? What kind of data should be exposed to a large language model? And how do you even orchestrate this whole process? There were so many unanswered questions, which over the last 2 years, there are a lot of tools in this space that started to evolve, and then this architecture is becoming richer and richer right now. So even then, enterprise-ready GenAI applications are very rare. And one of the biggest challenges is the relevance and contextual information for a specific question that the users are asking. Like, as a generic user, you could ask an LLM, what's the impact of reciprocal tariffs on US or any other country? Then based on what large language models know, based on all the news sources, we can get a generic answer like reciprocal tariffs potentially reduce trade deficits, but it could also increase higher consumer prices, et cetera, right? As a person who is in a supply chain, who is responsible for the supply chain resiliency in a particular company, the shipping industry, this answer isn't enough, right? So this is where RAG comes in. However, when you use all the unstructured data, vectorize it, and then store it in some vector database, you may still not be able to get the answer that you're looking for. And hence, you need a data structure that can capture the unstructured data, structured data, and understand your question and provide the relevant context for the large language models, so that you can get to answer something like, if I am a supply chain resiliency manager at a particular shipping company and asking what's the impact of reciprocal tariffs, then I want to understand what orders online are going to be affected, and what consumers or which customers are going to be affected. How do I efficiently change my pricing strategy or communicate the pricing strategy, et cetera, right? So this is where the graphs and graph technology comes into picture. And once we can accomplish the extent, or once we can accomplish this accuracy, relevancy, and completeness of the results at this scale, then we will be able to truly deploy enterprise-ready Gen AI applications. And my talk today is going to be how can we leverage knowledge graphs and companies' graph databases like Neo4j to start from what we have seen to go and build out truly enterprise-ready Gen AI applications, right? So, but how do we get there? How do we get from just understanding or just getting a ballpark answer or within the vicinity or relevant text versus accurate, factual, and contextual answers? If you look at your data sources, the data sources are all over the place. Like there are unstructured data, mixed data, and then structured data. Mixed data is where you may have some structured data with free-form text as one of the attributes, or you may have a totally unstructured data but with some metadata on the document as a structured format and so on. So if you look at the unstructured data, the latent representation of the unstructured data, which is possible by vectorizing the text form, is okay, is great, because now we don't have to do exact match, exact search on the text. However, we can only do do similarity between the text, two text phrases, but we cannot really understand the semantic um, closeness between those two, right? Or other than the textual description, you won't be able to use the other forms of metadata to say how similar they are. And hence, let's call it a lexical graph on this side. And a domain graph is where everything is structured. We have stored data in RDBMS, relational databases, and even document databases where everything is indexed, key value pairs or tabular columns, etc., which is something like a domain graph. But to get to the truly enterprise-ready Gen AI applications, take advantage of the advances in the large language models and different um, uh, architectures, we have to, or the data that we should use or we will be using is mixed data. And given the data storage or data structures that we have, none of the data structures are other than a graph data structure can be able to capture both forms of data, structured and unstructured data. So when you model data as a graph, then you start to see these things coming together. In a graph, it's a simple data structure that can capture entities in your data as nodes, and then the connections between entities as relationship between nodes. And then the properties, all the metadata associated with those entities become properties on those nodes. This compact building block will help you represent this data and then keep this unstructured and structured data coming together. So unstructured data, which is in the form of text, can be stored as properties on the nodes or relationships. Latent representation of the text, which is a vectorized form or an embedding, can be stored as a property on the node or on the relationship. And everything else like strings, numeric values, lists, etc., they will also be stored on the nodes, which can be used to represent different parts of the data. And then you can also use multiple relationships that connect between two entities or more than one entity, which can help you to represent how these entities are related to each other. I have a few more examples as we go forward, but this is the basic building block of a graph. When you think of a graph, don't think of a chart where you have an x-axis, y-axis, and then have some lines and then shaded areas. Those are all charts. The graph that I'm talking about is a data structure that can be used to capture this data. And now, if you really dive deeper into how do you actually represent data, then there are many different graph shapes that you can build. One is, for example, if you have all structured data, like there are these movies that are directed by certain people, and there are actors acted in certain movies, and the movie belongs to a genre, or movie is rated by a certain user with some description on the rating, etc. You can represent the data in like this, and which we are calling it as a domain graph, where you're building this graph from the structured data. Or if you start from your chunking process, unstructured data, then you can also store that they process unstructured text as a document as a node with the URL, title, and any other metadata of the document as properties. And these chunks, which are the pieces of text in the document, can be connected back to the document as a part of those documents. And you can actually make it even more explicit, saying that here is a document that has multiple chapters in it, and chapters have sections in them, and sections have subsections in them, and subsections, the text in the subsections are chunked, and these chunks are connected to each other. Now, if you ask this question, now if you have a question where the semantic similarity of the embedding of this chunk and this chunk both are matched with the question, immediately with the graph, you already know that these two chunks are the part of the same document and they belong to the same chapter. So even though your chunking is not smart, you should be able to use graph traversals to understand that they belong to the same context. Hence, they can be used to combine to give you the answer. So some of these nuances are not captured in other databases like vector databases or, or document databases. And these things make a difference when you're thinking about building truly enterprise-ready applications. And so what are knowledge graphs? Knowledge graphs are these graph data structures, but with the emphasis on the knowledge graphs is on contextual understanding, not just how things are connected to each other. There are also the nodes that represent concepts, events, and other contextual information, like any other taxonomy that you have in a retail company. Let's say when you go to a retail company like Home Depot, there are these aisles that has different parts, and these parts are also sorted based on different types of, like, hardware, and then the bath hardware, kitchen hardware, etc., etc. So the taxonomy can also be captured in the graph, so that when you ask a question, okay, I'm fixing this in my kitchen, what hardware is associated with this kitchen um, um, fixture, and then you can easily traverse the graph and then pick them up without really suggesting something that goes with the bath hardware and then saying, yeah, this looks very similar. Let's go put it in the kitchen panel. So it's not knowledge graphs not only capture the data in the form of a graph, but also have other things in them like concepts, events, and then all the connections between them, how they're related to each other, etc. So why is this important? Because this is the thing that I talked about in the first slide. When a supply chain resiliency expert at a company asks about what happens to the reciprocal, what's the impact of reciprocal tariffs, then instead of giving a generic answer, we should be able to give the answer like, okay, this product belongs to this assembly, is being affected because the price on that product is going to go up since it is coming from this country with so and so reciprocal tariff. So to that level of information is required for enterprise grade GenAI applications. And hence we need a knowledge graph to represent all these types of data together and connected. So now what is GraphRAG? A GraphRAG is where this graph is used in the process, in the RAG process, right? So where, or in the RAG pipeline, where when a user asks a question, whatever the data source we are using to provide context for the large language model, we will be that data source will be a knowledge graph, so that you can have a better relevant and contextual responses for a given question. So this is where the transformation comes in. GraphRAG transforms your GenAI applications by taking advantage of rich graph data structures. And the interesting thing that I'm seeing now and also working with customers is multimodal RAG. When it comes to multimodal RAG, again, the data comes from different forms, even though there could be chunks of audio files, there could be chunks of video files, transformed video files, audio, text, video, and then a combination of both, and then have a document with images embedded in them, etc., etc. So all these things, when come together, provide much more richer data landscape for your GenAI application to take advantage of. And knowledge graphs provide a platform for capturing this multimodal data. And then when you use GraphRAG, the idea is you should be able to retrieve knowledge from the graph. And this is where Neo4j comes into picture. as a graph database provider, Neo4j, our company, has been working on providing this tooling to enable users, application developers to easily integrate these GraphRAG pipelines, build out and integrate GraphRAG pipelines with their existing applications. And there are a bunch of retrieval patterns, like you can directly go and extract the similar vectors and nodes associated with them. You can continue from there to graph traversal and so on and so forth. I'm going to talk a little bit more about those in the next slides. Okay, so now the question is, now GraphRAG is great, but what can you give me an example? So if you look at an example of what happens when you start using not just the vectorized forms of text, but also the relationship between entities, when we can see this as an example here. If you consider an agent navigating commercial contracts, when you have these commercial contracts, then if we simply vectorize the text, then we can still ask some questions, because that's unstructured data. We can still ask some questions, but the questions are limited to certain types of questions, like what contracts mention non-compete conditions. That's an easy thing to answer, given the latent, given the embedding generation capability of full phrases of text by these large language models. But then once we start going beyond that type of questions, beyond search type of questions, to more context or relevance type of questions, like find all employee non-compete clauses with no expiry date. So then we need to understand what an expiry date means, which is properly a property on the document. And then it should not, I mean, you cannot simply vectorize and ask for an expiry date. It is a filter that needs to be used to provide relevant results. And this is where you should need both entity types and different entity types, and a way to model these entities beyond simply vectorizing text. So most of the databases now, like RDBMS and Postgre, for example, or MongoDB, or even Neo4j, can provide these entity modeling with vectors combined in the same place. But if you also think about how these go beyond those types of questions and ask what organizations incorporated in the USA have perpetual employee non-compete clauses, and who are the other parties that also have these similar non-compete clauses, then just simply filtering entity properties is not going to cut it. You have to think about how other entities are also connected to these entities, and this is where graphs really shine. And once you have the graph as a data structure and GraphRAG as the methodology to retrieve data and provide context to the large language models, then you can start to go beyond simple search questions on the left-hand side to even more appropriate and relevant and contextual questions for an enterprise, and then transform your GenAI applications. And in the next few slides, I'm going to quickly go through some of the examples, some of the slides, which will show you how the documents are converted into graphs. But again, this is just to reiterate the point, reinforce the point that simply chunking unstructured data, vectorizing it, and searching is only going to give you a certain level and entities. But if you also include relationships, then you can start getting better context from the same data that you have. After this one, I'm going to also walk you through a couple of notebooks that I have to show you the implementation of this. So bear with me. If you once I go through these slides, then I can switch over to the Python notebooks with some code to show you how it is done. And so this is an example of a RFP analysis GenAI app. So if you think about a RFP document, RFP documents, or like any other document, can have a bunch of structure, some bunch of text in it, but organized into some structure. Could be 10K documents from financial reports, or RFP documents, or maintenance manuals, or any other document that is relevant to your company, SOP, whether you're a manufacturing company or a pharma company. These documents have some structure and then some unstructured data in them. So if you look at a document, something like this, and when you represent that in a graph, then you start to see the graph, the document come up like this. So it is the RFP document. At a high level, these sections of intro, objectives, and proposals. and then breaking down the structure of the document, and then the content chunks are down here as leaf nodes, which is or which are the pieces of text that are uh, extracted from the blob of text under that subsection. Once we represent this graph and vectorize it, then the advantage of that is we can now search across these content chunks in the vector space, as well as use these relationships to go traverse across the graph. And this is one document. Now you have hundreds of documents, thousands of documents. Then this document and these chunks, if they're similar to the other chunks in the other documents, then these relationships can also span across these document subgraphs, and then these content chunks, when they're connected to the concepts and the entities, for example, if this is an insurance manual, then there is a glass damage or some kind of equipment, mechanical damage related claims, then those becomes more of the topics that you want to organize your documents into. That becomes a knowledge graph. And then when you go back to the questions, like when you're actually retrieving these, for example, if you want to ask this question among all the employees, who is the main respondent of this AWS RFP, then we can use the same question, and then you can start to see these, like this is the response from ABC company, signed by so and so person, and he is the general manager of the company, and the context is extracted from those chunks. And the step number one is you can still use vector index and Neo4j to get that number of chunks. And then we can start the graph traversal and then go up and then get an understanding. And all these content chunks are connected to the same node called company, and it doesn't have anything related to a proposal or any other objective of that particular RFP. And then you can start using that traversal to collect all that, which will help you in explainability. And then you can actually use graph patterns, which is one of the retrieval mechanisms, to go as high or as wide as you want. At the same time, one of the things that many of these applications really um, um, suffer from, or the data structures don't have a way to provide fine-grained access control. If you think about a vector database, and how can you enforce access control on vectorized forms of text? You have to post-process it. You have to filter it after you find the results. But when you're finding the results, you just have to let everybody search for everything in your knowledge repository, which means that you are letting anyone with like a low-level employee who is only responsible uh, for their projects is also able to search the financial documents from the C-suite, because you are vectorizing everything and then searching. However, when you apply the filters later, you may not even end up with any results at all. Or if this particular person is actually trying to search for his documents, but he may not be able to find it. So, but the fine-grained access control and providing fine-grained security is really, really important aspect of building a GenAI application that can be truly used in enterprise. And this is where you can take advantage of the knowledge graphs and provide these pre-filtering, post-filtering, as well as graph traversals. You may not want to hit the vector index, or you want to do hybrid searching on the vector index as well as your keyword search. And then you can also use graph algorithms in data science to go do brute force search on the community of those community summaries, etc. So you can have different methodologies, different ways to provide this fine-grained access control. So you can keep out and then not even traverse those documents that this particular person doesn't have access to. So finally, putting it all together, when a question is asked to the application, it will be converted to an embedding vector using an embedding model, and we can do vector embedding search in the vector space. And you can also use the result and start from those anchor points, go traverse the graph, and then even find additional information in the graph, and then or filter it down or expand the result set depending on what we want to do. And then we can, any other LLM here, Bedrock LLM is just an example, but any LLM you are using in this pipeline should be able to give you this graph, right? So this is one of the very common retrieval patterns in the GraphRAG methodology. Then you can get an answer like the main respondent of RFP is so and so, general manager representing ABC, and then here is the source that you found this information, and here is what the other RFPs that this person has responded to. What are the skills that this person has? Whether this person has other things that you want, you can go further and do further analysis, dive deeper into the data, and then get more information there. So that's one of the common patterns of knowledge retrieval. But again, there are a few different ways to retrieve knowledge from knowledge graph. And here is the blog post that talks about GraphRAG Python package. We have a Python package, Neo4j GraphRAG Python package, which has all these different abstractions and then also integrations available. So you can use it in your applications and then embed these retrieval patterns into your application. So the first one that I talked about is vector hybrid, where you start on the embedding, you start searching in the vector space and then go do traverse the graph and get more information. On the other hand, you can also use text to cipher, rely on the large language model's capabilities to transform your natural language to query language, and then you can get information from the database, which is much more um, uh, accurate and better compared to text to SQL, because the format of the query language that Neo4j uses to extract data from this knowledge graph. And then we can also use other forms like query focused summarization and then generic traversals. Like when it comes to defining tools that can be used in conjunction with your other frameworks like agentic frameworks and MCP, then we can use these pre-coded graph traversal patterns and then parameterized queries as tools to do specific tasks on the database, and you can expose those tools to your MCP client so that we can take advantage of these graph traversals and then incorporate them into your applications, which I'm going to show you in the demo that we are going to talk about. Sorry, we are waiting. I mean, we'll have all the questions at the end. So please, if you have any specific questions, or if you have any questions on related to the content on a specific slide, let me know. Then I can go back to the slide and then we can talk about it. And the topic of my presentation is transforming GenAI applications using knowledge graphs and Neo4j. So sticking to that topic, we talked about what these graph data structures are, what's a knowledge graph, why do you actually need a knowledge graph, and then what kinds of data. As an example, we went through an RFP agent, looking at the retrieval of knowledge from the graph. As I was telling you, we have a Python package, Python GraphRAG package that you can use to integrate these GraphRAG methodology, GraphRAG pipelines into your application architecture. Now, GraphRAG and agentic architecture, when you put these things together, this is what I was talking about. We have the data sources, and then the processing is done based on whatever orchestration framework you want to use. LangChain could be one, or Llama Index, or any other chunking strategies you are using, or if you have any NLP pipelines, or if you have any large language model backed extraction pipelines, all the processing of the data. And then once it's stored in Neo4j database, then we can take advantage of all these retrievers, retrieval methodologies. Like we can do full text search, we can do text to cipher, or vector search and graph traversal or hybrid search. And you can also use graph algorithms in Neo4j graph data science library to enrich the context in your graph database and also use one of these traversal techniques. And then when you use these coded patterns or define an agent that can take advantage that can take the schema of the graph as the LLM to generate the relevant cipher statement. You can actually use all those agents and tools available to those agents, and then incorporate all of this into your application architecture. And here's an example application that's built by my colleague. And it's called Neo Neo, it comes from our database Neo4j, and Converse is, you're talking to the database. Neo Converse, which is uh, which gives you a basic architecture for uh, incorporating GraphRAG pipeline and or bringing together the agentic framework and GraphRAG for your applications. Again, the arrows here is going to show you user asks a question. This Neo Converse calls the LLM with the question, the tools available, and the context. Then the LLM agent parses the intent of the question. It finds the relevant tool, and then either it gets a cipher agent. If it is like if it is a natural language to cipher tool that gets selected, then it just gets a cipher agent. Otherwise, it goes and then picks up one of the specialty tools, user-defined tools, and then it executes the retriever method, extracts the results from the database, sends the entire context back to the large language model, and then it generates the final response. And then you can also use another thinking loop in between, so that if the inquiry is not fulfilled, then it goes back to this loop, and then it can actually ask the question like a validation in the pipeline, saying that is the question properly answered? If not, let's go back and regenerate cipher, etc. So here's an example, and here's a blog post that talks about how do you implement this, take advantage of GraphRAG and then agentic architecture together for your GenAI applications. And one of the really interesting and important topics that is being discussed is agentic memory. So when you have these agents, multiple agents that you are deploying for doing different tasks in your application, and then tools that are available for each of those agents, then it's also really important for us to understand what these agents are doing, and then logging the conversations, logging the workflows, as well as making the agent remember what was the question asked and what was the context that was passed in the previous conversations. With the long context windows, and then all these large language models now are enabling memory inside a conversation, inside a session. So which is called short-term memory, excuse me, short-term memory. And these are limited to one conversation or one session, right? But it is not enough for enterprise applications. We need long-term memory. So the long-term memory with graph data structures, one of the other advantages is you can keep the temporal evolution of any state using a graph data structure. And then by using these relationships with timestamps and the property graph model enables you to store the lineage, like what happened, what was the first question asked by the user, what the agent did, what tool did it pick, what sources did it pick, what answer did it give, and then what was the follow-up question and what is the follow-up answer, so on and so forth. You can have these chains, conversation chains, that can be used for multiple purposes. And these are different types of memory that you can think about. Writing memory, so which is near real time or just backend. What's happening, and semantic memory, like if you want to add some facts to the conversation, then the LLM has to understand those facts, not just the context, combine those two, and then give give the response. And these facts are something that has to be stored in memory. Like, for example, if you learn something that, uh, like, I don't know, Dallas is the city in state of Texas. It is a fact. And then what happens is when you are answering some question, these facts append to get appended to the conversation, and then you are asking about what's the shortest time between Dallas and then flying to New York or something. So you know that these are not in the same place; they're in different states and so on and so forth. And then there's all semantic memory, and then you have episodic memory. Like, there is a conversation that happens, and you learn something from that conversation, and you want to use that in the next episode. So even modeling episodic memory or procedural memory, like what action to take when a certain type of events have happened, and mainly temporal memory. All these kinds of memory becomes really, really important when you're designing enterprise grade Gen AI applications. And hence, we need a data structure like a knowledge graph to be able to support your Gen AI applications and transform them so that you can truly take advantage of the advances in the generative AI. And here is an example. Here is a blog post by my colleague Alex Gilmore that talks about this modeling agent memory and how Neo4j can help you get to that state, that advanced state of uh, Gen AI applications. And all the buzz about MCP, we have two implementations that you can use right away. To these two MCP servers expose one MCP server exposes memory, capturing Neo4j memory, where you can read the graph, create new facts, etc. This is mainly used for semantic memory. Um, but on the mainly used MCP server is Neo4j Cipher, which by default gives you the Cipher database agent that converts natural language to Cipher. And also, it has two other tools that can read and write Cipher, read and write from the database. So combining these, we can start using, we can start building these GraphRAG pipelines. So again, we have so many testimonials from different people, different customers in across industries. Mainly the this one I really like because what with GraphRAG, you have an audit trail. You know where what the agents have been doing, what was the excuse me, you know what the agents have been doing, what was the data that's being used for generating answers, etc., and so that you can maintain the integrity and reliability. It is a healthcare customer, so that's also one of the important application. So this again, just to recap, we talked about the knowledge graphs, and then the data structures, mixed data. Why do you need mixed data? Why do you need a knowledge graph as a data structure? What are the different retrieval mechanisms in GraphRAG, and so on and so forth. Now, this is all great. This is all sounds like amazing in theory. So, as a company, we also have been working with different customers, as well as our colleagues have built some blogs and code examples. So today we are in this workshop. We are going to go through the code example, and then you can also clone the GitHub repo and start taking advantage of that. You can fork the repo or even go and do things by yourself. Um, if you have, are there any questions in chat, Shawari?
Yes. So one question is creating a knowledge graph from structure
Mhm.
and unstructured could require to build or require an ontology to support the graph maintenance. Any insight how to deal with ontologies?
Yeah. So even without this Gen AI or large language models, without talking about large language models or generative AI, Neo4j is a company. We are a 12, 14-year-old company, and we've been talking about how do you build property graphs to capture your data, as well as use label property graph model to model your data as a graph. So if you have any ontology that describes your domain, you can bring it and model it in Neo4j. So how do you build it? We have these tooling in Neo4j ecosystem that can help you bring data into Neo4j and then build a graph. Property graph data model is pretty flexible in the sense you don't have a structure like a rigid structure. Like if you have an RDF store, so RDF has a specific triplet structure, and the stores have stores, they store those triplets in a certain form, right? Whereas in Neo4j, which is built on label property graph, the model itself is pretty flexible in the sense you can start modeling based on your domain, how your domain looks, and then you can bring these ontologies, structured ontologies as well into the graph. With the before large language models, when you're trying to break down your unstructured data and then start bringing into the building a graph, we relied heavily on entity extraction using natural language processing pipelines, custom ML models or NLP models, and they're really great. You know, they're great. They work, but they weren't really flexible. And with large language models, you can actually engineer your prompt to provide the schema of the graph and then provide the text and then generate these nodes and relationships that you want to persist in a graph. There, you can also use your structured data, that is ontologies, or and any other factual data that is structured and unstructured, and merge all of those things together in a single knowledge graph. And Neo4j provides a lot of tools there, like Knowledge Graph Builder is an example that you can use to play with your unstructured data to a graph. And then Neo Semantics is the tool that is available for bridging the RDF ideology and RDF type, um, or RDF structure and RDF stores, and bring the data over to Neo4j and load CSV. I mean, if you have the data is in CSV or it's Spark data frames or Snowflake or any other place, then we have ETL that's available to bring data into Neo4j and then build out the graph.
Yeah, thanks. Right now, I saw one question. So once the question comes, I can ask.
All right. Okay. So let me go to this. Actually, I'm not running this live. I'm not running this live today, but I mean, I can just wanted to make sure that I don't run into any uh, OpenAI rate limit criteria here. But I want to walk you through this this GitHub repo. And just for Neo4j product examples, I have a lot of other examples that you can take a look at. And this is free for you can just pull these code from the repo. Like, let me copy this and then put it in chat. Yes. Here we are going to take an example of an employee graph. And the employee graph is, think of these employees as, employees having skills, different forms of skills. And then they are coming from their resumes. And a resume would probably look something like this. So we start from an unstructured data. And then this unstructured data, we'll process this unstructured data and then also combine it with some and then organize it in the form of a graph so that we can take advantage of some of the interesting questions one would ask if they have access to an employee. They could be an employee, or this could be a staffing or an organization, or even you going through different resumes to answer specific questions. But the premise here is every person here has a resume, and this resume is kind of structured. Or sorry, it's all text with different formats here. And then there are about 30 resumes here in this data. You can take a look at it. And what we did is, when we first built a graph, we uh, we extracted these data using large language models. There are 3 notebooks here in this repository here, which I'm going to walk you through. these notebooks talk about how do you retrieve knowledge from Neo4j. And the other pieces of this, the other parts of this repo show you how do you actually build the knowledge graph and so on. So once you build the knowledge graph, when here we are defining, we are using the OpenAI and then having and then build a prompt template and then the relevant extract the relevant data from the text using some functions that we want to extract the text and then provide a format to OpenAI, and then we extract these pieces like a person name, skills, etc. And once you extract it, then it's going to look something like this. So here is a person. Here is a person. He's a security engineer. He belongs to Department of Engineering. And then he has a skill Python, proficiency and programming, and his skill AWS, and so on and so forth. And he accomplished something. He built something. He built a zero trust authentication system. And then he built something else. He led a project. He shipped a product, and he also published a paper. He presented at some conference. He won an award. And then he has different companies. He worked at different companies and so on and so forth. So this is the extracted version of the resume. And once this resume is loaded into a graph, then it looks something like this. So the model of the data in a graph looks something like this. So here's a person. He knows he has a skill, and we
I think
encapsulate. Yes.
I cannot see. I'm still seeing.
Okay. Can
Yeah.
you see it? Yes. So here is a person who has a skill, and this person has published, built, or led different relationships to a thing. That thing could be an award, a paper, a product, etc. And this thing is in a certain domain. It could be security, it could be application, and it is of a certain work type. So this itself explains the whole process. Like for example, if you click on build, then if you see here, Miguel Santos built this product, which is a fraud detection microservice, another like REST APIs for e-commerce, and it's an inventory management system, and you can start to see different pieces of data here. So once we have this data here, of course, we can also look something like this. We just don't specify anything, but we'll say about this. So you start to see a graph that connects the different pieces together. Like here is a work type called system, and here is the person. Here is another person. So you start to see that these are not isolated points, but this person knows leadership, and this person also knows leadership. And there were many other people who might have listed leadership on their resume, or here's a team management. These are different skills. And then these are different things that they built, microservices, and so on and so forth. So the resumes that we saw are not simply chunked and vectorized, but not only that, if you look at a person node, then each person node is represented by some metadata, and the text is the resume, the free-form text, the concatenated text in the resume, and this is the embedding of the text that's been stored as node property on this one, and all the other metadata associated with the person. And if it is a skill has a name associated with it, and some ID, and so on and so forth. So this is how the graph is structured. And once the graph is structured like this, then again, let me switch back to this tab. So then we can start retrieving data using agents. Again, the agents is a new thing in the architecture. But if you don't think of agents, it's a simple retrieval pattern from the database, but you can encapsulate the retrieval pattern and then define an agent that uses that retrieval pattern to retrieve data from Neo4j. So let's take a look at how do we do that in Neo4j. So to give you an idea, I just showed you the resume, and then what did we extract from the resumes, and how did we build that graph, and what is that graph? Here it is. And you can go to Neo4j. When you run this code, you can create a new free instance in Neo4j Aura, which is our fully managed version, and then input this data into that database. Um, uh, Input this extracted data into that graph database so that you can explore the graph as well. Right. All right. So once you module one, here it is. Okay, so we'll be using Google's Google ADK, Agent Development Kit, and then we'll be using Neo4j GraphRAG and then OpenAI LLM for this one. And then we'll use Light LLM from Google Advanced Agent Development Kit to interact with OpenAI. And we connect to Neo4j using the URL password, and we do this. And once we load these documents into Neo4j, like we did, we take the PDFs. Once we take the PDFs, and then we can use OpenAI embedding model by calling OpenAI embeddings. This is available from LangChain, or you can use any other orchestration framework. You should be able to connect to OpenAI to generate an embedding for a text, and then using the driver here. Yeah. Once you have these embeddings, then you can use Neo4j Python package, Python driver package, and then call the database, and then start loading all the data into Neo4j. That's what I did. And also, once I loaded the data, I created a vector index, which uses HNSW to index those vectors with some other parameters like any other, what dimensional vector are you using, what kind of similarity function are you using, etc. And there are some parameters that you can use to improve your vector indexing and vector search capability that can be accessed through this Python driver and create this index in Neo4j. Once you index that, then you can give it a name for the index called text embeddings, and then you're done. You have the data loaded into the graph as nodes and vectors and index those vectors. And then once we do that, we can create a vector retriever agent, which is simply looking at the user question, converting it into a vector embedding, and then searching it in the vector space. So this is the basic functionality, which is equivalent to any other vector database, right? So basic functionality. We'll be calling the vector retriever function in Python GraphRAG package, and then referring to that particular index, and then taking, like, I want to look at the AI research as a query text, then it's going to go and grab 5 resumes that has relevant topics about AI research. So it is like Isabella Rosi, Amanda Foster, and then Aisha Patel, and so on and so forth. So these are few people, top 5 resumes that have better similarity with the query vector. You can do the same thing with LangChain. So you can see using LangChain and integrations from LangChain, you can use search in the documents and then get the search documents with. All right. So I hope you did you hear what I talked about LangChain?
Yes.
Right. So now we can use the MCP implementation of Neo4j. No, the MCP we'll talk about a little bit later, but using Google's agent development kit, we can start wrapping this into an agent, and then we'll use OpenAI GPT 4.1 as the LLM, and then let's call it a search agent, and then give a description, and then we'll give these search documents, which is the function that takes this user query
goes and gets the Neo4j schema. Um, this user query generates an embedding, takes the embedding, goes and queries the Neo4j vector index, and then brings back the documents. And this agent is doing the thing by when we give the search documents as one of the tools to this agent. And then we can run the agent with this. We can call it Mr. Ed. One of my colleagues is Ed, and then we just named this Mr. Ed, who does this, who is the search agent. And then when the session is started, we can start asking the question: how many Python developers do I have? A simple basic question like the one that I asked you when we were searching. Then you start to get the answer. You start to see the answer here. And then it says that based on the search, I found 5 employees with significant expertise on hands-on development. Each result content, it explains the logic. And then who is this person? Full stack engineer, and so on and so forth. So this is still based on vector search, but it's still much better when you when you have these everything stored in one place. And then we can talk about who is most similar. It looks at the vector search again, and then the answer is based on different employee resumes. Elena Popo, because they have operated AI system development. One thing to notice here is this is based on what LLM thinks they're similar, but this is not based on the actual data in your graph, why these two people are similar. This is just, you just have to take the answer, but you won't be able to explain how these two people are similar to each other. And again, if you can summarize this Cyberdyne's technical talent, Cyberdyne is a company, Cyberdyne's technical talent and skills distribution, then it just goes and it goes through the entire data in the database. And then it kind of summarizes the technical talent and skills distribution. Of course, as the database scales, once you have lots and lots of data in the database, this is probably not the right query to ask, because it's probably going to run and not finish because of gigabytes of data. However, we should be able to have some guardrails around these queries that we can put in place to go and access the relevant context only, and then give the answers. Now, if we go to the next one, so this is about vector search with agents. So the first notebook is, when you go and download this notebook, you'll start to see that we are only taking the data, vectorizing it, storing it in Neo4j, and searching the vector index. But we are not using other kind of retrieval mechanism, which makes it even more interesting. And it is here in this particular notebook. With graph construction and retrieval, one of the questions we had earlier is, how do you construct a graph? So we can use the tooling in Neo4j GraphRAG Python package to specify the schema that you want, to specify the entities and relationships that you want to extract from a piece of text, and then use the large language models to extract that, and then load it into a graph, which we call it knowledge graph builder. You can take a look at it, and then of course sometimes it's not. If you have much more domain specific graph, then you may have to do some post processing to make sure that the graph faithfully represents your domain. But if it is more like a search type application, then it should be out of the box. It should be good to go. But take a look at it, and then you'll start to see how interesting it's going to be. So as we talked about in the beginning, when you're taking resumes and just vectorizing it and then generating some recommendations, it's not enough, because that there's no value of graph in that. The graph value comes into picture when you start to make it more explicit, make the relations more explicit. Like the example, like the database that I showed you earlier. When you use, when you make this graph, so when you have this data, like instead of simply vectorizing text on person, if you start to make these relationships more explicit, how do we construct that? This is what shown here in this notebook. So we take the person who knows the skill, who did a thing, but we will flesh out this a little bit into the schema. And then once we take the extracted people data JSON file that I showed you earlier, and then in the graph construction, it's simply connecting to the graph using Python driver, and then pushing the data into the graph by creating some basic database rules like constraints and then the keys, and then you just go through those records and then start storing the data into Neo4j. Once you store data into Neo4j, you'll see the graph that I showed you earlier, where you can query the relationships and so on and so forth. So once we have the graph, so all this code here is showing you how do you upsert those relationships, like what is the relationship type that's being extracted from the large language model, from the text, whether it's a thing, person related to thing, person related to domain, thing in domain, etc. And then you see a graph like this, which I showed you earlier. And now what we want to do is we want to take advantage of a different retrieval mechanism, right? So one of the retrieval mechanisms is you search in the vector space, find the anchor nodes, and then go to the graph and then get more results, and then enrich the context for answering the user question. The other types of retrievals is you use patterned cipher or parameterized cipher statements, parameterized queries, and then expose them as tools so that your agent will determine what tool to use in real time and then pick the tool. So we'll stick to the MCP protocol, and then using Neo4j MCP, we will expose those tools to the we'll expose the tools that are provided by Neo4j MCP server, and also additional tools to the orchestrator using Google, this agent. What is it called? Google agent, Google's ADK or Google MCP toolset, and so on and so forth. This terminology is changing, and then obviously you may have access to Microsoft version of it or AWS version of it, or some other tool associated with it. But at the core, this is going to be the same. At the basic level, this is going to be the same. So we are going to define a database agent, and then we'll give it a description, some instructions, and then tell the database agent that there are domains, work types, and skills in the graph, and then you can access the knowledge in the database. And also can give some instructions of not to return embedding properties because they are bulky, they are not useful. And then when responding to the user, there is certain again, this prompt is pretty flexible. You can go ahead and then define your own prompt. But when you define these tools in the MCP toolset, we will be using in the first step, we'll be only using the MCP server from Neo4j, which has tools like get Neo4j schema and read Neo4j cipher. So what it does is when the session is started, when you ask how many Python developers do I have, in the previous question, it used the vector index to go and find the similarity between the question and then the expertise. But here, because we are using the MCP server, it actually calls the tool and then gets this cipher query, match person, knows skill name Python, and return the count as Python developers count. And it uses this tool called Neo4j cipher. So what is the advantage of this versus that, right? So if you are looking in the vector index and the vector space, you are getting answers, but those could be diffuse because anybody who says Python and something else, then it'll be counted, and then there will be some similarity associated there. Maybe high, maybe not. Maybe it may interfere with your results. In this case, because we already have a structured form of our resumes, data extract from resumes, it is going and doing an exact database search. It is looking for people who have listed Python as one of their skills in their resumes. In that case, you have a much more deterministic or much more boxed result than something that may not be relevant to you. So there are some disadvantages also. It is not fuzzy, it's actually exact. But the um, advantage of using large language model here is you are not crafting the query. Large language model is actually giving you the cipher query with all those where conditions if needed and filters if needed or expansion if needed, and so on and so forth. So this is a continuously evolving thing, and then the LLMs are getting better and better at it. But you can take advantage of is right away. Use the read Neo4j cipher, and then the tool. And it also, I queried the employees who have direct relationships in the company's knowledge graph. This means, and so on and so forth. So this gives you much more explainability. You can go back into the graph and then start to see this together. And of course, the answer is there are 28 Python developers. It's like, okay, so what? Yeah, great. There are 28 people who know Python in the company, so it's amazing. If I want a Python project, then I can submit an RFP and so on and so forth. And then the next question, we also looked at who is the most similar to Lucas Martinez. When we asked this question in the vector search, then the skills, then it just said, okay, this is based on so and so skills, right? But here, if you look at the query that's being written, it's actually much more interesting. So it matched a person named Lucas Martinez, and it collected all the skills that Lucas has, and it matched all the other people who has also skills that are matched, who has listed the skills, and then it used an intersection, and then it ranked those people based on the overlap similarity between the person Lucas and then the other people in the database. So which is much more explainable. Like, you say, okay, Emilio Popov is similar to Lucas Martinez. How? Because the LLM said so. Versus, here are the 6 people, like Sarah here has 9 overlapping skills. And then Sarah has 9 skills, Lucas has 11 skills, Sarah has 9 skills, and they overlap on 6 skills. So based on the skill similarity, they are similar to each other. And that makes it much more explainable. And any enterprise application without explainability or auditability is going to be not approved, right? So this is where things start to get really interesting. And then we can also start to go into this summarizing, etc. But then I want to go to adding expert tools. Now that is, we simply relying on text to cipher capabilities of large language models, which are evolving. But you can also add more tools. Like, what do you mean by find similar people? I just don't want to rely on simple overlap skills, but I also want to look at something else. I want to add my own logic. And so I can write a cipher query that does that, or and then give more weightage to not just knowing but also leading some project related to their experience, right? And find similarities between people. Here again, these cipher queries they look really complex, but cipher as a query language is much more expressive. So if you don't understand these queries, don't worry about it. There are really nice, simple introduction courses that Neo4j provide that can help you quickly pick up if you really are looking forward to write some cipher. So what we are doing here is we are going to take those, make it more explicit, make the query more explicit, make the definition more explicit for finding similarities between people, like how these person knows skill, and so on and so forth. And then also you can get a person's resume, get a person name. These are simple tools. Get person IDs and a talent agent. So now now you take all these tools and then put a talent agent together. Instead of a DB agent, let's call it a talent agent. And this talent agent is a little bit better human resources agent that can help with skill analysis, talent search, team formation, RFP, so on and so forth, right? And then these are all the different tools that we just defined. And then we also include the default MCP tools available from Neo4j. And then we just orchestrate this agent. Once we do that, then you can ask this question, how many Python developers do I have? Then it picked the same agent, read Neo4j cipher like it did earlier, even though it has access to all the other tools. So which means that it is okay. It is a very generic question. But when you ask the next question, who is most similar to Lucas Martinez? then it did not go and did the same thing. It didn't go and do the same thing like it did in the previous round, but instead it picked a tool. It picked a tool called person name. It just went and picked up Lucas, and then it actually did a lot of other work and picked different tools. And then it says Lucas Martinez and Elena Popov has several skills, highly aligned domains, especially AI. And here I used expert similarity tool that ranks people based on the counts of common skills. Not only that, work types and accomplishment domains. So vector search gave us Elena Popov, but it did not explain why. But after doing this, even Elena Popov came back up as a similar person. Now we have more explainability. And again, you can start to see these, and you can see summarize my talent, technical talent, and skill distribution, which means that as a company HR manager, if you're asking this question, then it just goes through summarizing Cyberdyne's talent, technical talent, and skills distribution. It goes and it writes down these things, and this is all coming from your knowledge base, and this is all factual data, right? 28 people in Python, 16 people know SQL. There are 14 middle managers, and other people use DevOps, artificial intelligence skills. There are so many activities that happen. There is a breadth of employee and so on and so forth. Then there's a retrieval logic and explanation that comes with it. So you start building out these applications by wrapping these agents. Now these agents can also talk to the other agents, but as long as these independent agents can talk to Neo4j database, they can access data independently, and then you can use ensemble models, or how these agents communicate with each other, handle handle data, whether you're using A to A type protocol or MCP, or combination of both. All these plugging these retrieval mechanisms, and using knowledge graph as the database, as the data structure to capture this multimodal data, and then using these tooling that we provide from Neo4j to extract data from Neo4j can help you incorporate GraphRAG into your GenAI applications. And by incorporating GraphRAG, you can truly transform these applications, right? So if you have any more questions, I think now we can take questions. We only have 10 minutes, but I can stay longer if you have any questions. And please feel free to unmute, or maybe, I don't know, Sharvari, would you be moderating, or would people be unmuting themselves?
Yeah, if anybody wants to ask, they can also. But I can ask you a couple of questions till somebody is ready to ask. So one question is, how does inference time, like time to predict, compares with the traditional RAG versus graph base, especially when the knowledge graph size increases?
Yeah, that's a good question. How does the inference time changes? So the thing is, here, the tooling, the tooling that's provided by Neo4j is accessing the graph database to return the data from the database, right? So like any other database, the database queries usually run really, really quick. Like if the database query is running longer than few seconds, which means that it is accessing lots of data. You don't call it a database query, it's a data warehouse query at that point. The database queries are really fast, and if you already have the patterns, like I said, summarize the content for all the people in my company. If your database has millions and tens of millions of nodes, and then all the nodes are the same type, then obviously you need to touch all the data. So in that case, there are a few things that you can optimize. It's a wrong query. Maybe you should not look at that query like that. Or first you should remodel the graph so that even if it's a right query, you should not time out. So there are these optimizations that are available to improve the inference time. But whatever we have seen so far, the database retrieval time is not at all the bottleneck in the entire RAG pipeline. LLM is the slowest one in the RAG pipeline. Whether you're using LLM to convert natural language to cipher, or whether you are asking a large language model to summarize the text from the results, that is the slowest one in the whole pipeline. So we never saw any inference time challenges with Neo4j database.
So that means it's comparable to the technology.
Yeah.
So another question I have is about hallucination. How does this help or reduce than the traditional technology? Help us to reduce the hallucination?
Yeah, so RAG in general is the methodology we use for reducing hallucinations, right? So that is number one. And the additional advantage that we get when we use graphs or graph data structures are, first of all, when you break down your data, when you store your data in a form of a graph using structured or unstructured, you're already making the relationships very explicit. So I took an example of Dallas in Texas versus New York, right? So there may be it's like we are when we extract data from Neo4j, we only extract data what's inside the database. That's the context that's provided to the LLM. And also what happens is with these graph reversal techniques, with parameterized cipher statements and cipher patterns and tools that we define, we are explicitly mentioning what part of the graph you are touching and what data you're extracting. So you can go and take a look at the data that comes out versus data that's actually in the database. So that's where the there's a very, very less chance of hallucination there. Then what's the next step is when the data comes out of the database and then now you are handing it over to the large language model. That's where your prompt engineering comes into picture. The better the tighter the prompt, the better the guardrails in the prompt, the lesser the hallucinations. So where the advantage of a graph database is compared to a vectorized vector database is not just the semantic similarity between the vectors, but also the proximity or the closeness in the graph structure can also be used as a filter to reduce the to reduce hallucinations or to improve accuracy of your responses.
I think we are almost done. I saw one more question. Okay. So the question is, how would you combine data from existing RDBMS along with unstructured data? Do we need to remodel existing data models in RDMS sources in Neo4j?
So here the underlying assumption is when I'm talking about this knowledge graphs, the underlying assumption is you're bringing your data into Neo4j. Okay, so your unstructured data, when you process it, chunk it, vectorize it, and extract entities and all, they will be stored in Neo4j. The actual blobs, the actual text files, they can be stored in an S3 bucket or a Google bucket anywhere else. But the extracted form of the documents and the embeddings are stored in Neo4j. Now you have your structured data in the RDBMS, in RDBMS database. What we typically do is we don't bring all the data over into Neo4j because graphs are really suited for applications like what is the data that you want your application layer to access, like in this case, large language model. You can use this as a connection between your RDBMS tabular schema and your unstructured graph in Neo4j. You can actually do that by creating representative nodes in the graph that point to your RDBMS tabular schema. But if you think it's going to help in bringing some dimensions of those table into the graph, then it will be easier for you to understand where the data is, and then you go and then get the data, retrieve data from the actual RDBMS. So there are different forms, different ways to integrate these two technologies. And we also see some people overlaying Neo4j on top of their tabular schemas, but that also works, and it makes a lot of sense. But at the same time, you'll get a lot more value when you start bringing some of the data into Neo4j.